Hi there! A while ago I found this capacitance decade on eBay. It's a type DK4SV and it was made in Denmark by a company called DANBRIDGE. As you can see, it has 3 rotary switches for capacitances in 10 steps, one each for 1 nanofarad, 10 nanofarad and 100 nanofarad steps, and a variable capacitor from about 50 picofarad to 1000 picofarad. The stated accuracy is an amazing plus minus 0.5%, plus minus 10 picofarad, but the variable cap is only plus minus 2%. While I did not find a manual, I did find an old DANBRIDGE catalog of their decades which had some useful information. So I have the DK4SV, which is a precision S model. The 4SV has 3 decades made of polystyrene capacitors, which are better than the polycarbonate types they use in the A models. The 4th cap is, as we know, an air capacitor from 50 to 1050 picofarad. The accuracy figures are measured at 1 kHz, and the graph shows that at higher frequencies the capacitance will increase, especially for the larger 100 nanofarad or 0.1 microfarad types, which increase by 1% at 20 kHz. The smaller capacitors are much less affected. There's also a hint here how the decade is made. DANBRIDGE uses a common method of 4 capacitors in a 1:2:5 ratio to make each decade. I explained how this works when I repaired my other decade. I put up a link to that video if you have not seen it. With 4 capacitors in this ratio, you can get values from 1 to 10 by switching the appropriate capacitors in parallel, in other words, adding their capacitances. However, the multi-level switches needed for this are complicated. I assume there is a trade-off here where the saving of needing only 4 expensive precision caps outweighs the cost of the switch. So far so good, but I have a problem with the whole concept of this decade. Let me demonstrate. The rotary switches are all set to 0, so the only thing active is the variable capacitor, and yes, that works just fine. The dial is not terribly accurate, but I guess I could loosen the screw holding it and get it closer. I set it to 100 picofarad as best as I could, and when I add 1 nanofarad from the first rotary switch, I get quite accurately 1.103 nanofarad and so on. My problem is that variable capacitor, which is always active and added to the result. While the rotary switches are producing highly accurate capacitances by just selecting the switch position, I can't use this decade for anything without first setting that variable cap to some known value that I need to measure, because the dial is at best 2%, but at the moment even worse. Honestly, I'd rather not have that variable cap. Let's have a look inside. The enclosure is quite nicely constructed. You need to undo the 2 screws on the front and 1 on the rear to remove one of the side panels. With that gone, you can just slide out the front plate, which contains all the components. There seems to be something like a varistor across the 2 terminals to protect the cap from too high voltages. Then we have a stack of 4 smaller caps connected to the 1 nanofarad rotary switch. Next is a can containing 4 caps with a common terminal connected by wires to the 10 nanofarad rotary switch, followed by 2 larger cans, one with 3 and the other one with just 1 cap, connected to the 100 nanofarad rotary switch. The largest can is the only one where some text is visible, 0.5% as advertised, but not much else. Initially I was toying with the idea to simply permanently desolder the connection to the variable cap, but then I thought maybe someday I may want it. So I revised my plan and investigated if I could add a switch, allowing me to easily include or remove this cap from the overall result as needed. A good place would be right between the cap and the first rotary dial, about where the red QA stamp is. And through the magic of drilling, a switch appears at that position. I try to desolder the connection to the air capacitor, but the yellow wire has been tightly wound around the blank wire, so that's not going to work easily. In the end, I decided to use snips. The remnants could be wound off now after reheating, but in the end I did not bother. To keep in the style, I ran a yellow wire from the switch to the air cap and deliberately not wound the wire around the blank wire. I'm confident this joint will be just fine. The previous connection needs to be extended to reach down to the switch. Okay, it's not as pretty as the original wiring, but nobody's going to see it once the unit is back in the box. Does everything still work? With the switch closed, the air cap is in play as before, and the range is unchanged from slightly above 50 picofarad to a little above 1000 picofarad. If I flip the switch, the air cap is no longer in circuit and the meter now reads 25 picofarad. Not 0, because there's always some stray capacitance, but with a fixed 25 picofarad offset I can live. It's much less likely to change compared to the air cap, and the value is small enough to be zeroed out in the meters. Trying the different switch settings and you can see how well the capacitance decay works. By the way, I used this old battery-powered capacitance meter I found on eBay quite some time ago because I find it to be very accurate, and in this case I can perch it above the decay, which makes filming a lot easier. Here's the spec sheet of that vintage capacitance meter. It can't do anything else but capacitance, and its maximum value of 2500 microfarad is pretty limited by today's standard. It has its own way of measuring, which is not a sine wave, but according to the manual equivalent to 100 Hz sine wave measurements. However it does it, it's marvelously accurate, with 0.2% plus minus 0.5 picofarad plus minus 1 digit. Still, it's pretty old and has never seen a recalibration since it left the factory, so I decided to use two other LCR meters for comparison, the UT612 and the IM401, both at 1 kHz as specified by DANBRIDGE. In all cases I zeroed out the meters when the switches were all set to 0. I think it's pretty clear that the three meters are basically agreeing with each other. Interestingly, all meters show the same behavior. The error, small as it is largest for the 1 nanofarad range and drops significantly in the 10 nanofarad range, and again, but not as much, in the 100 nanofarad range. I think this reflects the problem of measuring very small capacitances. Just putting your hand close to the measurement leads changes the picofarad values. But overall, I think the capacitance decay works as it should, and I'm much happier with it, especially after adding the switch. If you like my videos, don't forget to like and subscribe and help growing this channel, and consider becoming a Patreon. The link's in the description. Thanks for watching.